So, hopefully you see my iPad. We're going to be doing lesson 4.3, which is about logarithmic functions. And then we're going to take that and we're going to kind of flip it. So let's get started. So we had originally done exponential functions. So that's what an exponential function looks like. That b with the power on it equals some number. Well, the opposite of that is called a logarithmic function. So we have this, the base is next to the word log, standing for logarithm. The x is the number that we are evaluating. The answer to a logarithm is the power. So you'll notice that this is the power. And this is our base. And this is our number. Okay. It is an opposite function of a power. It is similar to the way of thinking of multiplication versus division. They go hand in hand. Without the multiplication, you wouldn't have the division and vice versa. So keep that in mind as we're doing those. So in the first few problems here, we are taking a logarithmic form and just writing it as exponential. So let me show you what to do. So if we start with number 1 here, first you want to identify the base, then you want to identify the power, and then you want to identify the number. So we know that the base to that particular power is going to equal the number. So that's kind of what we're going to use to convert. So 16, that number, is base 4 to a power of 2. So we've converted it. That's it. Okay. Sometimes we are going to need to write it in that 16 equals 4 squared, or we won't be able to do much to it, or actually so just keep that in mind. Okay, let's do the next one. So again, we need to identify the base, the power, and the number. The base is going to show up next to the word logarithm. So that's our base. Here's our number. The answer is our power. Once you have identified the 3 things, we just have to put it in the correct form. Now, I just like to leave the number where it's at, then write the base to that power. And so 0.2 is 5 to the negative 1 power. Let's do another one. So we're going to identify the base. Our base is 8. We're going to identify our number. Let's make that look a little better. Our number is 1. And our power is 0. So that means the number 1 is equal to a base 8 with a power of 0, which we know is true. And then finally our last one here, identify what's your base. Our base is 23. Our number is 1. Our power is 0. So our number 1 is equal to our base 23 to a power of 0. So that's just kind of how we convert that logarithmic equation into an exponential. And sometimes the exponential is going to be the route we really want to take. There are a few times where we go backwards, but it's really important to be able to know how to go that direction. Does anybody have any questions about 1 through 4? I figure those tend to kind of make some sense, hopefully. Now let's look at going the opposite direction. Okay, so now remember what we know. A base to a power equals a number, and then if we want to flip that around, I put the log on the number with the base next to it, and it's going to equal the power. Okay. So again, we want to identify what's the base, what's the power, what's the number. So if we look at number 5, our base is 2, our power is 4, our number is 16. So on the 16, we're going to put a log base 2 of the number 16 is really saying what power on a 2 gives me a 16, and that's why the answer is 4. Let's do it again for number 6. Our base is 27. Our power is 1/3. Our number is 3. Okay, so remember what we're going to do. On the number, we're going to write the word log with that base. And then the answer is our power. So what does that mean? Well, that means if I have a base of 27 and I put a power of 1/3 on it, I am going to get an answer of 3. And so remember, the answer of a logarithm is always the power that you would use to get that. It's the power is your answer. Let's take a look at this one. Here is our base. Here is our power. Here is our number. So we are going to take the number. We're going to write the word log, and within the corner under, or right by the G in the word log, we're going to put our base, which is 1/4. That's really saying what power would I put on a 1/4 to get the number 16? And the answer is -2. Now let's discuss why it's -2. Well, the negative is going to flip that fraction over. So if you flip the fraction 1/4 over, you are going to get 4. The 2 is going to square it. So 4 squared gives us the 16. So that's why 1/4 to the -2 power becomes such a large number, because the negative flips it, making it 4 over 1, or 4. The 2 squares it. 4 squared is 16. Does anybody have any questions about 5, 6, or 7? Okay. Now, we are going to take, and we are going to actually use logarithmic notation, but think of it in a power sort of way to help us evaluate these logs. Okay, so let's look at number 8, dealing with the log base 12 of 144. What that means is, what power, because remember the answer to this is a power. So we're really saying, what power do I put on a 12 to get the number 144? Well, there's a variety of ways to think about that. If you were good at multiplication from back in the day, you might recall that that is 12 squared. 144 is 12 squared. So the power we would put on a 12 to get 144 is 2. So the answer to this is 2. Let's look at 9. So we're asking ourselves, what power would we put on a 64 to get an 8? Now, the only way we're going to put a power on a larger number and make it smaller is one of two ways. Either we have to flip something and use negative exponents, or we have to use fractional exponents. So I'm going to show you two different ways. You might recall that 8, let's think about it this way. The square root of 64 is 8. Now remember, we're trying to relate the number 8 back to the number 64. So the square root of 64 is 8. Now, somewhere along the line, I'm not sure exactly what section, but we mentioned that we could rewrite that as a 1/2 power. So we just found the power to put on a 64 to turn it into the number 8, a 1/2 power. A 1/2 power is the same as taking the square root. So the answer is 1/2. Now there's another way to do this problem, and I'm going to do it to the left of it here, because I want you to kind of see multiple ways to do it. So one thing you can also do, since we know the number 64 is 8 squared, we can take out the 64 and replace it with 8 squared. The square just sets next to the p. It multiplies by the p, following rules of powers. And so we get that 2p would equal 1, so p is equal to 1/2. So there's multiple ways to do these problems to get a correct answer. We either had to think of how 8 relates to 64 or how 64 relates to 8. One way or the other, we had to make these kind of match up in order for the problem to work. Any questions about number 9? Let's move on to number 10. So remember, the answer to every logarithmic problem is a power. We are saying for this one, what power do I put on a 3 to get 1/27? Now, we can relate these things because 27 is 3 to what power? Tell me, 27 is 3 to what power? Can anybody tell me? 27 is 3 to what power? Exactly. Very good. It's 3 cubed. So if we think about this as 3 cubed for a minute, that's going to be a good start. Now we also can think about what can we do to a power to get this thing out of the denominator. What could we do to that power right there to make that thing flip? Can anybody tell me what we would do to that power to make that flip? Yes, negative exponent's sole purpose is to take something and make it its reciprocal. So if we write this as 3 to the negative 3, we just found the answer. What power did I put on a p or on a 3 to flip it and cube it? Well, the negative is going to flip it, the 3 is going to cube it. The answer is negative 3. So you always are trying to relate to your base, get the bases to relate to one another so you can think about what we would do to get that number. So if one is a fraction, one is not, usually your answer is going to be negative. And then you just got to kind of relate the two things. Does anybody have any questions about 8, 9, or 10? Okay, now, excuse me, logarithms were created. There was a guy, and I think it was way back in like the 1700s. He wanted to be able to do bookkeeping. He was a bookkeeper. His father, I think, had a big merchant business, and he was doing all these books by hand. And he created the first type of logarithm called the common log. The common log was a way to take very large numbers and write them in a much more succinct, smaller way, so that you could have like the number 10,000 becomes the number 4 in log base 10. So if you ever see, well, you're very rarely going to see log base 10. Instead, what you're going to see is just the word log. So if you just see the log 10, because our number is a base 10 system, there's technically an imaginary little 10 sitting there. You know how in a square root, we don't see the little 2, but in a cubed root, we do? That's because the square root is common. We use it all the time, so you never see that little 2 there. A logarithm, the most commonly used one is our common log, base 10, because it's what our number system is based on, base 10 number system. On a calculator, on most calculators, if it just says the word log, this is the kind of logarithm they're talking about. And so this is one time, if you had like the log of 17, you could just put that into a calculator. Another type of logarithm that we're going to be using is the natural logarithm, and its base is an e, you see right here. And I really don't know why, but they use the abbreviation for natural log, ln, the natural log. E is that same e we saw in our exponential functions, that 2.71828. Most calculators are going to have a log button and a natural log button. So please, you can only use those when dealing with log base 10 and log base e. Okay. So for problems 11 through 14, you can enter these into a calculator, but I want to show you how to do it without. Okay. So let's start with number 11. For 11, since this is it doesn't show our base. Technically, it's a base 10. And so 100 is 10 squared. Excuse me. So what the question is they ask, what power do I put on a 10 to get 100? Well, we just found it. 100 is 10 squared. So the answer is 2. Number 12. Number 12 is also a base 10 question. This is, let's see, tens, hundreds, thousands, 10,000s. So this is 1 over 10,000. So that is 1 over 10 to the 5th, which is 10 to the negative 5th. So the log base 10 of 10 to the negative, is it 5th or 4th? Wait, 1, 2, 3, 4. Yeah, I'm sorry, that would be 4th. That's a 4. That's a 4. And that's a 4. Sorry about that. So what power do we put on a 10 to get 0.0001? That's a negative 4. Logarithms are used in science a lot because they go hand in hand with scientific notation. So if you know anything about scientific notation, logarithms are sometimes used. Sometimes they're used for very, very small or very, very large numbers, depending upon, what the application is. I know that there are some biology applications that use logarithms. So that's base 10. Let's take a look at 13. So we have a natural log of e to the negative 3. Well, technically, that's the log base e of e to the negative 3. And when these are next to each other like that, the answer is the power. Because what power do I put on e to get e to the negative 3? Negative 3. Here, that's asking the same question. What power do I put on e to get e to the 10th? 10. So there are some things, and we'll go over those rules in a minute as to why they end up working out that way. Okay? Does anybody have any questions about those? Now, if we are doing a log, that's a log base 10, and that power or that number is not exactly a power of 10, like 100, 1,000, a million, a millionth, a hundredth, something like that, then you can use your calculator. So problem 15 and 16, we're going to use the log button. For 13 and 14, if you don't see an e sitting in a natural log, there's no way for you to evaluate it without a calculator. That's like 17 and 18. We don't see that little e sitting there, so we can't just jump to the answer. So instead, we have to use a calculator. Now, let's follow the instructions. The instructions for 15, 16, 17, and 18 say round to 4 decimal places. So let's start with 15. The log of 200. So you're going to it depends on the calculator. Some calculators you're going to enter 200 and then hit the log button. most scientific calculators nowadays, you hit the log, then the 200, and rounded to the nearest 4 decimal places, we're going to get 2.3010. Now, you can check these very quickly. If we put 10 to 2.3010, you're going to get really super close to 200. You're not going to get exactly 200, but you're going to get super, super close. You might get 199.9 or something like that. Okay, let's do 16. Again, you have to use the log button, please, not the natural log button, or it's not going to work. This is a decimal value, so we should expect to get a negative when rounded to the nearest 4 decimal places. We get negative 1.1308. So if you want to check those on your calculator, you can verify that they do work. Now let's take a look at 17 and 18. 17 and 18, you have to use the natural log button. So if you're going to use the natural log button, most calculators have a natural log button on it. For number 17, rounded to 4 places, is 5.2983. We could check that very easily by taking e to a power of 5.2983, and we should get something super close to 200. If not, then you know you did something weird. Now let's look at 18. The natural log of 1.005. And it's 0.0050. Okay, does anybody have any questions about the log or natural log problems that you see here? Okay, so there are some rules for any type of logarithm. To get an answer of 1, you are going to have to use a power of 0 because of the fact that b to the 0 equals 1. So this works for any log, whether it's a natural log or a log base e, log base 10, whichever one. Here you'll notice if the b's match what power on a b keeps it a b, that's a power of 1, because b to the first is equal to b. What power on a b gives us b to the x? That would be x, because b to the x equals b to the x. And here, this is kind of a hard one to wrap your head around, okay? So what power on a b, well, okay, let's start here. What power do you put on a b to get x? Is the answer to this. That's the power. And then you put that power on a b, so guess what you get? You get x. Now, do you have to know that? Not really. What you need to think about is the fact that if you see this relationship where they're right next to each other like that, they cancel out, leaving us just with x. So there's, so here they cancel out, leaving us just with x, and here, see how they're kind of reversed? So that's just kind of something you need to know. And that works, again, whether they're natural logs or e's, or any kind of logarithm. So we're going to use some of those rules to simplify here. So let's start with 19. What power do we put on a 19 to keep it a 19? Well, 1. So for number 20, we don't see a base. Can anybody tell me what the base is for number 20 when we don't see it? What is the base? Yeah, exactly. If we don't see that base, you're just going to put a little 10 there. I like to show that 10 for my own brain. I'm like, oh, okay, that makes sense. So the question is what power do I put on 10 to keep it a 10? And the answer would be 1. Natural log. That's really log base e. And so it's saying what power do I put on an e to get an e? So the answer is 1 again. So 19, 20, and 21 are 3 different ways that you can see where a 1 would occur. Let's take a look at 22 and 23. Both of those are saying, what power do I put on my base to get 1? Well, unless it's a 1, the only way you can put a power on a 273 to get it to be a 1 is if my power is equal to 0. So both of these, no matter what my base is, if there's a 1 sitting there, you had to have a 0. 24 is our first example we are seeing where these two match, but we have a different power sitting up there. So we're asking ourselves, what power do I put on 30 to get 30 to the 10th? And the answer would be 10. And then finally, 25. That's really what power do I put on an e to get e to the negative 12? It would be negative 12. So those are ways that they cancel out very nicely. 27, 26 and 27 are both that kind of strange example I was talking about. So these match kind of in the opposite direction. So that is a 14. These match in the kind of that opposite direction. So the answer is 5. So kind of neat. Any questions about 19 through 27? Okay. So we had graphed exponentials for 1 or for 2, one of those. Now we need to graph logarithms. Logarithms, you really want to be super careful about the x's that we're going to choose. For many of our functions we've done in the past, we choose positive 1, negative 1, and 0. In these functions, we can't do that, unfortunately. So, first thing you want to do is you want to notice what is my base. And then let's start kind of with the center of our graph. It's not really a center, but kind of our good point to start with. We're going to start with 3 to the 0. We're going to go 3 to the negative 1 and 3 to the positive 1. Now, I tend to always do those 3. Sometimes I will go back. I mean, they're wanting me to fill up the form, so I'll keep going back. 3 to the negative 2 and 3 to the negative 3, 3 to the second, and 3 to the third. Now, what are those values? Let's go back to the middle. 3 to the 0, that's really 1. This is 3, 9, 27. So this is 1/3, 1/9, 1/27. Okay? But look at the fact that we chose these numbers on purpose because they were related to a base 3. So let's start with the middle. What power would we put on a 3 to get 3 to the 0? 0. And then what power would we put a 3? Let's go down the chart. What power would we put on a 3 to get 3 to the first? 1. What power would we put on a 3 to get 3 to the second? 2. What power would we put on a 3 to get 3 to the third? 3. So this one's going to be negative 1 and negative 2 and negative 3. You might recall if we were graphing, I'm sorry, not that. If we were graphing that, those x's and y's are completely and perfectly turned around. Why? Guess what? These are inverses of one another. So the points on our exponential should be the reverse of our points on our logarithm. So for a logarithm, I'm very careful as to what x's I choose. I always choose powers of 3. And I go 3 to the 0 and 3 to the 1, and 3 to the 2, and 3 to the 3. And then I go backwards. 3 to the negative 1, 3 to the negative 2, 3 to the negative 3. Okay. And then if you go ahead and graph them, which they've already nicely done this for us, you get this function. This function, you might recall that our exponential function had a vertical asymptote. Well, guess what? Our logarithmic function has a vertical asymptote at 0. So I'm sorry, our exponential function had a horizontal asymptote at 0. Our parent kind of function of a logarithm will always have a vertical asymptote at 0. If we look at the basic form, I'm just trying to think of a good way to write it. They might give this to us later. I don't know. But if you have this value here, where x minus h equals 0, so x is equal to h, that is always going to be our vertical asymptote for this graph. That's kind of our boundary that we will never kind of cross. Our h and k would still do what it always does. It would move it left and right or up and down. The a value in front could possibly stretch it or flip it. Okay? So there's 28. So let's now look at, well, before we go on, anybody have any questions about 28? Okay, so let's take a look at 29. So we have some changes and transformations to our function. So let's just kind of focus on what we would normally do. So our base is 2. So normally our base 2, I'm not going to do all of these. I'm going to just do these middle 3, and then you'll get the idea. Normally I would plug in 2 to the 0, 2 to the first, and 2 to the negative first, okay? But we've got this 1 plus x here. No, I'm sorry. For some reason, every time I write a plus next to an x, I get weird, strange, I write strange things. Anyway, so what is 2 to the 0? 2 to the 0 is 1. And if I subtract 1 from both sides, I get 0. So my first x value is 0. Now let's plug in, do 2 to the first. So that's 2 equals 1 plus x. X equals negative 1. And if I plug in negative 1, that's 1/2. So if I subtract 1 from both sides, that's negative 1/2. So my good x values are kind of strange. Now remember, this lined up with 2 to the 0. This lined up with 2 to the negative 1. This lined up with 2 to the first. Okay. So if we actually plug those in, if we plug in negative 1/2, we get inside the parentheses 1/2. What power do I put on a 2 to get 1/2? Negative 1. If I plug in 0, I get 1. What power do I put on and I have something else I have to do in a minute, but what power do I put on a 1 to get, what power do I put on a 2 to get a 1? And that would be 0. And then finally, if I plug in negative 1, I get 0. Wait, let's see. I think I did something wrong here. Oh, I did. Look at my work right here. I subtract 1 from both sides and I get a positive 1. 1 plus 1 is 2. What power do I put on a 2 to get a 1? And that would be 1. Now, one thing I haven't done to any of these yet, there's a little plus 2 on the end here. So I have to, following order of operations, add 2. And so if we go to graph it, so here's the point negative 1/2, 1. Then 0 is at 2, and 1 is at 3. Sorry, we got stuck here for a second. And so let's analyze what happened to this graph. So the 1 plus x equals 0 at negative 1. So it shifted the whole entire graph to the left one. So remember when I was talking about the vertical asymptote, this particular graph has a vertical asymptote at negative 1. The plus 2 just lifted it up 2. See, the normal log base 2 of x would be down 2 units from where this one is. So basically, it's just that log base 2 of x moved to the left one and shifted up 2. So you can do the original if that helps, like what I did here in pink. You could have just completely graphed the original. The parent function is the log base 2 of x. You could have graphed that, and then based on transformations, you could have shifted it to the left one and up 2, and that works perfectly well too. So if that makes more sense, this is kind of a strange one to kind of wrap your head around. Any questions about 29? Okay, so here's what they were talking about. So remember, our A is going to reflect it across the x-axis. If it's negative, it might shrink it or stretch it depending on if it's between 0 and 1 or greater than 1. This number is going to move it up and down, just like we would expect. This number might possibly move it left and right. Okay. If you look at the logarithm versus the exponential, see how it goes across the line y equals x, because they're the exact inverses of one another. So the domain for our so this is the domain and range of the exponential. Here's the domain and range for our logarithm. See how the domain became the range, and the range became the domain. See how the horizontal asymptote became a vertical asymptote. And look at the point. This one had a point of 0, 1, so this one has a point of 1, 0. So they are complete inverses of one another. All the x's became y's and y's became x's. And so that's just kind of how their graphs are related. Okay, so here we're talking about domain and range. So they want us to write the domain and range in interval notation and write an equation of the vertical asymptote. So if you set x plus 3 equals 0 and solve for x, that is the equation for the vertical asymptote. Okay, if you look on the graph, we can see that it doesn't hit, but gets super close to the line x equals -3. So that's our vertical asymptote. Let's talk about domain and range. We do not plug in any x's over here. Our x's are from that vertical asymptote over. So our domain is almost -3, past it to infinity. Now remember, we write that almost -3 by putting it in a parenthesis. Now let's take a look at our range. This graph can get as low as we want. This graph eventually will get as high as I want. The range is from -infinity to +infinity. And you'll see that happen. That's the opposite of what 2 to the x plus 3 would be. Let's take a look at 31. What the negative did is it flipped it, but we still have an asymptote right here, because you'll see that's 0. There's no transformation. So the vertical asymptote is x equals 0. Let's talk about domain and range. We want all x's from here over, all x's from here over, not quite 0. We write as 0 in parentheses to infinity. Now let's take a look at our range. This graph will extend down as low as we want, go up as high as we want, and without skipping any values in between, our range is -infinity to +infinity. Does anybody have any questions about 30 or 31? So the domain of a parent function for a logarithm is everything from 0 to infinity. It matches this one. That is the parent domain and range. So only if we've moved the graph to the left will the domain shift to the left. The range will always be -infinity to +infinity for a logarithm. But there are restrictions into what values we can plug in. We cannot plug in negatives. There's nothing we can do to a number 2, like 30, base 2, nothing we can do to a base 2 to ever make it negative. Because negative exponents won't do it. That's just going to flip it, but it'll always stay positive. Here is, the question here is, what is the domain for x squared minus 3x minus 4? Now, technically there is kind of an asymptote here, But let's look at how we can discover what that is. We are looking for where x squared minus 3x minus 4. Yes, we are going to do that. Yep, you're one step ahead of me, Adam. Give me a second. We're going to look where that is greater than 0. Remember, we can only plug in positives. You can't plug in 0 to a logarithm. You can't plug in negatives. So we only want the positives. So next, let's try to factor it. So this is going to be x minus 4 and x plus 1. And you might recall that we did that plus minus chart. And here is another application for the plus minus chart. Set each factor equal to 0. Solve. Put it on a number line from least to greatest order. We're going to put open circles there because we cannot be equal to 0. And we're going to make this number line into a chart. On the side here, list out your factors. Now, we're going to get test values. So to the left of -1, I don't know, is -2. In here is 0, and in here is 5. Let's plug those values in. If I plug in -2, I get a negative. If I plug in -2 to x plus 1, I get a negative. I'm going to multiply these because remember, right here, they're multiplied. So a negative times a negative is a positive. Now let's plug in 0. I get a negative. I get a positive. A negative times a positive is a negative. Let's plug in 5. We get a positive and a positive, which is a positive. Now, I only want the positives because I just can plug into a logarithm positive things. So what is our domain of this? Well, it's from -1 to, I'm sorry, I totally have that backwards. We're going to go from -infinity to -1, and then from 4 to 5. They must have been counting by 2's here, because that would have been 1 and 4. Okay, so why is it 4 to 5? I'm so sorry. That should be 4 to infinity. There you go. Okay, so that is the domain there. We have one more problem to do in this lesson. Then we're going to take a little 5-minute break, and then we'll continue with the next thing. Okay, so let's look at 33. It says, the absolute magnitude m of a star is the apparent magnitude little m a star would have if it were placed 10 parsecs from Earth. The lower the value of the magnitude, the brighter the star. Our sun has an apparent magnitude of -26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of -1.44. The sun appears so bright because it is very close, astronomically speaking. The formula, m equals little m 5 log d of rho 10, relates the star's absolute magnitude, apparent magnitude, and distance from Earth in parsecs. Every time I say parsecs, I think of like Star Trek. But anyway, if Sirius, there we go. Sirius is 2.637 parsecs from Earth. So that's its distance. So let me write that down. So distance equals 2.637 parsecs. And the sun is, so we'll call that distance 1, and distance 2 is 4.887 times 10 to the -6 parsecs from Earth. What is the absolute magnitude of each star? So remember, the absolute magnitude we're doing is the large m. So we must have enough information for the little, for solve for the large m. So our sun has an apparent magnitude, so that's little m, of -26, that goes over here, I'm sorry, -26.74. Sirius has an apparent magnitude of -1.44, and so we want to look at the absolute magnitude, big M, for each. So we're just plugging into the formulas, all of that. And so for the Sirius, for the dog star, that is going to be -1.44 minus 5 times the log. So that would be a log base 10 of 2.637 divided by 10. Okay, so let me enter that into a calculator. Let's go 3 decimal places because that's the most I see in this problem, and so we'll just continue with that. Negative 1.44 times, or I'm sorry, minus 5 times the log of 2.637 divided by 10. And so the absolute magnitude of Sirius is 1.4544. Now let's do our sun. So for that, it would be negative 26.74 minus 5 times the log of that big decimal right there. Over 10. Okay, let me put that into the calculator for you. So negative 26.74 minus 5 times the log of that 4.887 times 10 to the negative 6 divided by 10 equals 4.8148. So there you go. I think they just wanted you to practice using a formula and that had a logarithm in it. So I guess somebody likes some astronomy, I guess. So there you go. There is our lesson on logarithms. Thank you for watching. Let's take a 5-minute break, and then we will be back doing 4.4. Okay, so thanks, guys. Give me a second, and we'll come back.